Okay, so touching on matter, it's either a pure substance or it's a mixture. Pure substances are elements and compounds. Where do we find elements? On the periodic table, PT, periodic table. Compounds are two or more elements chemically combined. And they are in a fixed ratio. What I mean by fixed ratio, let's say you have water. Then you have 2 H's and 1 O. No matter how much water you have, you will always have twice as many hydrogens as you have oxygens. Always, okay? These words right here are the important thing. Fixed ratio. Have a seat. You have Mr. McGregor? Here, you have to sign in. He wants to know whether you were here or not. And sit up front.
All right.
And take one of these. There's a lot of rules. All right. A mixture can either be homogeneous. I have to go this way just because. Homogeneous or heterogeneous. If it's homogeneous, it is a solution. And you'll see a little AQ after it, which means mixed with water. Okay? Homogeneous is uniform throughout. Heterogeneous, on the other hand, let's just highlight this. So this is all homogeneous. And then heterogeneous is going to be not uniform. Okay? And it's easy to separate. So things like a tossed salad, chicken soup. You can see the tomatoes, you can see the cucumbers, you can see the chicken, you can see the noodles. That's a heterogeneous mixture. What color haven't we used yet? Red? Okay, so that's matter. It says matter is classified as a pure substance or a mixture. A pure substance is an element or a compound, has constant composition, that's fixed ratios. If you want to write that right on here so that we have it, fixed ratios, and constant properties throughout the given sample from a sample to sample. You can use particle molecule models, diagrams to differentiate among elements, compounds, and mixtures. Let me show you some particle diagrams just to jog your memory. Let's do this. Make some boxes here. Okay, solid, liquid, gas. These are going to be pure substances. They're going to have only one thing in the box. Every time I reach my hand in there, I get exactly the same thing. Okay? So if I reach in, I'm getting one of these blue circles. Here I'm getting a blue circle. Here I'm getting a blue circle. They're all pure substances. If, however, I have something that looks like this, that's a mixture. Because if I reach into that box, I'm going to get a blue circle or a red circle. I just don't know which one I'm getting. Okay? Mixtures have varying proportions. I can have a lot of red circles and a few blue circles, or I can have a lot of blue circles and a few red circles. I vary in proportion. All right, oh, look at that. The proportions of components in a mixture can be varied. Each component in a mixture retains its original properties. I saw a question on that. One time they mixed iron and sulfur. Okay, and when they mixed them together in the box, the iron remained magnetic. What's the matter? And the sulfur remains smelly. That, that sulfur smell that I'm talking about? Dr. Skaggs probably had you sniff a rock or something. You know what I'm talking about, right? Okay, so iron and sulfur, if you mix them together in the same box, they still stay separate. But if you have a chemical reaction, let's say you have magnesium and oxygen, and a chemical reaction takes place and you make magnesium oxide, now this has different properties than the magnesium and the oxygen, than these. Okay, so this has different properties than these do. All right. Separating mixtures. There's lots of different ways. We can just do it by hand, by looking. Oh no! It wasn't charging before, so I don't know if it's on. So, see the little lightning bolt. Let's see what happens. If not, I'm going to have to write on the paper. Okay. We can just look at it. We can separate it. We can, let me do this also. Maybe that'll save me a little bit of battery. We can evaporate the water off from a solution. Example, let's say you had a beaker, and in that beaker you have NaClAq. NaCl is salt, AQ is water. So in here you have salt and water. How can I separate them? Well, I can get the water to evaporate, turn into a gas. What's going to be left at the bottom of this container is going to be the salt. Okay. We can filter. For Emily and Michael, just so you know, I'm taping this, so you'll be able to. I'm just gonna post it on YouTube, the video, so you'll be able to watch it again if you need to. If you miss something and I'm going too fast, just hit pause. Right. Pause me, okay? All right. We can also. What did I just say? Filter. Filtration. So let's say you have a funnel here, and you put some rocks and water through that. Well, what's going to come out the bottom? The water is going to come out the bottom, and the rocks are going to stay up here. The reason why the filter works is because particle size is different. It also works if solubility is different. Solubility is different. For example, let's say I have salt and rocks and water. Well, the salt is going to dissolve. The rocks do not dissolve. And the water is the water. So if I pour the salt, the rocks, and the water through the filter, what's going to come through this filter? The salt and the water are going to come through the filter. The rocks are going to be stuck up here. Now, down here in this bucket, I have salt water, NaClAq. How can I get the salt separated from the water? well then I can evaporate it. You see how that works? Because the rocks and the salt have different solubilities. All right, distillation. Distillation is the process of separating a mixture based on boiling points. So if you have a container, and in that container you've got water, and you've got this CH3CH2OH. What is that? My people should know. I don't know if you guys got to this yet in Mr. McGregor's class. It has an OH at the end. It is ethanol, good, which is an alcohol. Yeah, this is alcohol. All right, and this is water. Oops, I'm writing. Let's do water. Ooh, water. All right, what temperature does water evaporate? 100 degrees Celsius. And ethanol, let's make it 80 degrees Celsius. It's about that. Okay, so if I light a fire underneath this flask, Emily, you know what that is? No, what's this yellow blob that I just drew here? Oh, good. All right, just making sure you're awake. So this is fire, right? That means this thing is going to heat up. When this heats up, is it going to get to 80 degrees first or 100 degrees first? 80, which means this alcohol is going to turn into a gas. And it's going to start floating around up here. And it's going to go up here before the water does, because it gets to 80 before it gets to 100. Now, if I hook a tube up here, this is a tube, and as that gas travels down the tube, it cools off. It's going to go from being a gas to being a liquid. And then what's going to happen is over here, the drip, drip, drip that's coming out of this side is going to be pure alcohol, because the alcohol is what's going up over the tube. So distillation separates according to boiling points. The lowest one is going to boil first, then the next one, then the next one, then the next one. That's called distillation. Sometimes they even say the word fractional distillation. Don't let it fool you. Okay? That just means you're taking a fraction of whatever is in that flask out. It's just a fancy way of confusing you. Okay? It doesn't mean anything. You're still separating according to boiling points. All right, the last one that they have listed there is chromatography, and chromatography kind of looks like this. You got a piece of paper, you put a little dot on the end, and then the water that you just hit with the bottom of this little paper will start to move up the paper, and it will carry these dyes up the paper, and so they will separate out according to their different sizes. The smallest particles are going to travel the furthest, and the bigger ones are going to stay down here. Okay? Today is Monday, right? All right, any questions on that? We're good to move along? Okay, tell me if you don't need me to go over this stuff, I can do something else. The structure and arrangement of particles and their interactions determine the physical states of a substance of a given temperature and pressure. All right, I kind of already went over solids, liquids, and gases right here. Maybe solids, liquids, and gases. You should also know your diatomic elements. I'm dying. It is hot. Okay, what are your diatomic elements? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are your 7 diatomic elements. You have to know those. Okay? You need to know what on the periodic table are your gases. No, not everything that's to the right of the staircase is a gas. Okay? N, O, F, and Cl are gases. Everything in this column is a gas, and hydrogen is a gas. Then there's 2 liquids. There's iodine. There's bromine and mercury. Those are your liquids. And then everything else, iodine down, and everything else that's over here except for that mercury, are going to be your solids at STP. Draw particle diagrams. All right. Physical and chemical changes. Let's just go over that real quick. Physical change are things like solid going to a liquid, which is called melting. Liquid going to a gas, which is called vaporizing. Gas going to a liquid, which is called condensing. Liquid going to a solid, which is freezing. Solid going directly to a gas, which is called sublimation. Gas going to a solid, deposition. Those are all physical changes. And, oops, let me shut this off. When you look at something like H2O and it stays H2O, and it's going H2O solid to H2O liquid, that's a physical change. You did not change the substance. It's still water. Why is that so dark? Water, water. Okay? If, however, you have H2 plus O2 becoming H2O, let's make that a liquid and make this a gas and make this a gas. Okay? Now my reactants, which are over here, and my products, which are over here, are different from each other, then this is a chemical change. Because I am now dealing with a totally different substance. These guys are not the same as this. They have different properties. So that's number 4 on there. And then it says physical and chemical properties. All right. So what are some physical properties? Color, shape, size, density. These are physical properties. Chemical properties, things like ability to combust. That means burn. Reacting with an acid. To produce bubbles. Anytime you get something that you didn't have before, that's a chemical change. All right, I see on here it also says some common properties of the elements are found on table S. Let's quickly just refresh your memories on what's on table S. When you look at the top of table S, okay, you have ionization and electronegativity. We'll get to those later on. But you have physical properties like its melting point, its boiling point, its density. These are some physical properties of these particular elements. So just like we were just looking at a Regents a couple minutes ago, right? Didn't they ask us something about the densities? It said compare the densities. This is where you get that information from. Don't forget that that's there. Okay, any questions on that? All right, let's take a look at some questions. A sample composed of only atoms having the same atomic number is considered an element. A dilute aqueous potassium nitrate solution. All right, here are the key words. Aqueous and solution. If it says it's a solution, then we know it's a homogeneous mixture. Olivia, are you with me? Okay, so we know it can't be heterogeneous. It's a solution. Is it a compound or is it a mixture? Well, as soon as you see the word aqueous, we know it's a mixture. Because by definition, aqueous means mixed with water.
Can you go up a little bit?
Yep. Right here?
Yeah.
Okay. If I'm going too fast, just let me know. I'm just trying to get at least 2 units done today. Because there's a lot to do. Good, Michael? Mm-hmm. Okay. At which Celsius temperature does lead change from solid to liquid? If it's changing from solid to liquid, that is melting. Where do we find lead's melting point? You go right here, you find lead, which is going to be... Oh, lead, where are you? Right here. Okay. You look and see where its melting point is, which is this one, this column. So we're going to go down. And they gave us lead. It has a melting point of 600. 600 what? Kelvin. See how it says K right here? That's Kelvin. So we know that lead melts at 600 Kelvin. Well, if it's 600 Kelvin, they asked for it in Celsius. How do you change from Kelvin to Celsius? Yeah, baby. Kelvin minus Celsius. I'm sorry, Kelvin minus 273. Where the heck is that? Minus 273 is going to equal Celsius. So let's go ahead and do that. 600 minus 273. Okay, this is going to be a 7. This is going to be a 9. This is going to be a 2. This is going to be a 5, right? 327? Does that sound about right? 7, 8, 9, 10. 7, 8, 9. 3, 4, 5.
On the paper, it's 328.
What?
On the,
Yeah, it's going to be 328. Well, these questions are old. These are old questions. So it could be that they changed it on the reference table in the last, maybe it was 3601 in the last, but that's the closest one. So that's your answer. All right, chemical property of hydrogen gas. Chemical property means it has to be doing something. It's got to be changing. So which one of these gives us a chemical property of hydrogen gas? 1. It's burning. That's combustion. Combustion is burning. Burning is chemical change. Which element has the greatest density at STP? Where do we find that information? Gotta look on there. So let's look them up. Now, here's the thing. When you get a question like this on the Regents, this is called a giveaway question, right? It's just have to look it up. So we're going to find calcium. Calcium has a density of 1.54. It's right here. Here's calcium. This column is density. See it up there? Nora's like, got it. Okay? Do not be lazy bums. Make sure you write down 1.54 right next to calcium. We're looking for the one with the greatest. Don't try to remember them. Carbon. Carbon is going to be, doesn't have one. So let's put it a little dash there. Chlorine, 0.002898. 0.002898. And copper. Copper's going to be our answer. Let's just find it. 3.96? 8.96? Okay, I'll take your word for it since I didn't find it yet. 8.96. And so copper is going to be the greatest density. Okay, which statement describes the chemical property of magnesium? Again, chemical property is the key word here. So it has to be reacting or changing, so I'm going to go with reacts with an acid. All right, what's the most important words in this question number 7? 2 more different elements. What else? Fixed proportion. Okay, if it's in a fixed proportion, then what is it? Nope. Compound. Mixtures vary in ratio. Compounds have fixed proportions. What happened? Compound, fixed ratio, mixtures. I didn't write it down here. Vary in ratio. Let's write it just for fun because it's on tape now. Vary in ratio. This is why I don't leave this thing plugged up. Vary in ratio, because it starts to do those crazy things with the lines. Okay, continue right along. Which element is a solid STP and a good conductor of electricity? So we want a solid and we want a good conductor. So if it is a solid, that's most of the periodic table. If it's a good conductor, what do we know about it? It's going to be a metal. Okay? Good conductor, it's going to be a metal. So let's find the metal. Is iodine a metal? No. Is mercury a metal? Say what? Mercury is a metal. It's the only liquid metal on the periodic table. Oh, nickel's a metal too. Oh, but they said solid. Haha. This one's a liquid. Nickel is a solid. So nickel is our answer, not mercury. Okay? All right. The table below shows the mass. Am I going too fast for you? You all right? Okay. Just yell if there's a problem. Table below shows mass and volume data for 4 samples, blah, 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 blah. Which 2 samples can consist of the same substance? They gave us mass. They gave us volume. What can you calculate from mass and volume? Density. So let's go ahead and do it. Density is mass divided by volume. 30 divided by 60 is 0.5. 40 divided by 50 is what? .8. Okay. 45 divided by 90, 0.5. And 90 divided by 120, 0.75. Okay, so now I've got all the densities. They want the same substance. So it looks like it's going to be A and C. Is that a choice? That's good news. All right. Bronze contains 90 to 95% copper and 5 to 10% tin. Because these percentages can vary, Bronze is a mixture. At STP, which list contains a solid, a liquid, and a gas? All right, let's label them, I guess. HF, solid, liquid, or a gas?
Solid.
Looks like a solid to me. Remember, most of the periodic table is solid. So, HF is, where is it? HF, where are you? Here it is. Okay. Okay, that's a solid. It's not NOFCl or any of these. These are your gases and hydrogen. So it's a solid. So I'm going to put a little S above it. It's hard to see. Mercury we know is a liquid, so I'll put a little L above it. And helium is a gas. Oh, look at us. We got lucky. It's the first one we did. All right, just for fun. So this is our answer, because we wanted a solid, a liquid, and a gas. Barium is a solid. Bromine is a gas. Boron is a solid. So this one has two solids. So that's not the answer. Chromium, solid. Chlorine, gas. Carbon, solid. So that's not our answer. Selenium, Se, right here. It's a solid. Tin, solid. Strontium, solid. So it looks like 1 is our answer. Don't be afraid to write on your paper. 10-gram sample of which element has the smallest volume at STP? Okay, they're all 10-gram samples. We want the smallest volume. Standard, temperature, and pressure. How do you do this one? Got to look at the densities. So if we want the smallest volume, we want the, they gave us mass, density equals mass over volume. We want the smallest one of these. So I guess we can do them all if you can't see it. So let's write the densities, right? Aluminum, what's the density of aluminum? 2.7. What's the density of magnesium? 1.74. Let's do titanium. 4.56? 06? Okay. And zinc? Wait, I can't hear you. 7? 134. Okay. So, density equals mass over volume. Volumes are X. Mass is going to be 10. Density, let's do the zinc first. 7.13. Okay? 10 divided by 7.13 is going to be a little bit above 1. .4. Okay, so this is going to be 1.4 as a volume. Alright, that's the largest number. Now let's do the smallest number, magnesium. 1.74 equals 10 over X. X equals 10 divided by 1.74. I got 5.75. Okay, do I have to do the ones in the middle? No, because it says the smallest volume. Okay, so it's an extreme question. Extreme questions have to be extreme answers. You can't have one of these middle ones. So it's going to be number 4, zinc. You understand how I did that? All right. At room temperature, a mixture of sand and water can be separated by... How can I separate sand and water? Filtration. The sand is not going to dissolve. And the water is going to go right through the filter. That's filtration. All right, which particle diagram represents a sample of one compound only? So they're looking for a pure substance. Why'd you pick one? All the same. Good. A 1 mole sample of neon gas occupies a volume of 24.4 liters at 298 Kelvin and 101.3 kilopascals. Calculate the density of this sample. Density equals mass over volume. Okay. Did they give us mass? No, they sure didn't. So how are we supposed to do this then? What did they give us? A mole, right? And can you change moles to grams? It's not a lot of work. You got this. Okay, so you got 1 mole. And we have neon gas. How much does 1 mole of neon gas weigh? Let's round it to the nearest whole number to make our life easy. Do you see that? 20? Okay. So 1 mole is 20 grams per mole. That means I have 20 grams. If I have 20 grams and my volume is 24.4 liters, what's 20 divided by 24.4? No, it's less than 1. 0.819. Grams per liter. All right, an investigation. A dripless wax candle is masked and lighted. As the candle burns, a small amount of liquid wax forms near the flame. After 10 minutes, the candle's flame is extinguished and the candle is allowed to cool. The cooled candle is masked. Okay, see you later, go. Identify one physical change that takes place in this investigation. Is that physical? What's physical change? What? Which is? Oh my gosh, no. No. Hold on. What are some physical changes? That's earlier in the day. Where's physical changes? What are some physical changes? What is the candle doing? Melting. Good. Okay. So identify one physical change that takes place in this investigation. The wax is melting. That's a physical change. You still have wax, except it went from a solid to a liquid. All right. State one observation that indicates a chemical change. Here's your chance to shine, Michael. Chemical change. Burning. Good job. Burning. All right. Draw a particle diagram showing the change from a solid wax to a liquid wax. Use this little circle for particles of wax. Draw separate diagrams for the liquid and the solid. So let's draw the liquid here. Let's draw the solid here. Okay, could have went either way. Liquid, the particles are going to be down at the bottom of the container. You're going to have some room around them. Solid, they're going to be, and I did not write this down earlier. I should have, and it popped into my brain, but now it left. When you have a solid, these particles are arranged in a regular geometric pattern. They're nice and neat and orderly. That's the solid. This is the liquid. Okay. Base your answers to questions 19 through 21 on the particle diagrams. Ooh, they're getting hard to see. Which sample represents a pure substance? And tell me why you picked it. Okay, sample 3, why? All the same substance. So if I reach into that box, I'm always getting 2 white circles. When 2 atoms of Y react with 1 atom of Z, a compound forms. Using the number of atoms shown in sample 2, what's the maximum number of molecules that this compound can form? Alright, so Y is the black ones, and Z is the white ones, and I need 2 Y, so 2 black ones. I'm going to cross them up here. 2 black ones and 1 white one will give you a compound. Okay. 2 black ones and 1 white one will give you a compound. Can I make any more? Nope, I can't. So the maximum number of molecules of the compound that can be formed is 2 molecules. I can only make 2. I'll have some things left over. I'll have white, 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 and white. I don't know if there's one there. It's hard to see. White, white, and white, and a black one. Alright, explain why XX, this 2 right here, is not a compound. What's the definition of a compound? Different elements. Is XX different elements? No, they're the same. Okay, that takes care of Unit 1. Questions?